is Wednesday, July 15th, 2026, and this is the Neural Deep Dive. I'm Vector Kane, and I'm here to accelerate your cognition.
I'm Roxanne Stone.
I'm Leonard Cooper.
And I'm Alyssa Montgomery. We have a great show for you today.
Right. So, look, our usual daily roundup already dropped this morning, but we wanted to give this one its own space because we need to talk about the Sparse Mixture-of-Experts revolution, specifically the Llama 4 Scout architecture, in a way that actually makes sense.
Yeah, and since we spent yesterday talking about those HBM memory shortages and the Apple OpenAI bloodbath, it's actually the perfect time to dive into how we're trying to cheat the hardware limits. Okay, so let's just get into the weeds here. For the people who aren't living in a server rack, we're talking about MOE, Mixture of Experts. Basically, instead of one giant dense brain that fires every single neuron for every single word, you've got a bunch of smaller, specialized brains.
It's like a corporate office, sweetie. You don't call the CEO, the janitor, and the head of HR every time you need to fix a typo on a memo. You just call the person who actually knows how to spell.
Exactly. It's a switchboard. You've got this router that looks at the incoming token and goes, oh, this is a coding question? Send it to the Python expert. This is a poem about cats. Send it to the creative writing expert.
Right, and technically, the magic is in the sparsity. Like in the old dense models, if you had 1 trillion parameters, you had to do 1 trillion calculations for every single token, which is just, a total waste of compute. But with MOE, you only activate a fraction of the model.
Oh, if I may, it's important to distinguish between the total parameter count and the active parameter count. In something like Llama 4 Scout, you might have a total pool of 109 billion parameters, but you're only actually using about 17 billion per token.
Wait, so it's like the cheat code? You get the intelligence of 100 billion parameter model, but the speed of a 17 billion parameter one?
Sort of. I suppose that's the goal. It's an activation ratio of about 15%. So you're decoupling the knowledge capacity, which is the total size, from the compute cost, which is the active part.
Now, here's the deal. This isn't exactly new. We've had Mo for a bit. But the problem used to be that the models were lazy. They just pick 1 or 2 experts and use them for everything, while the other experts just sat there doing nothing.
Right, the routing collapse. It's like a bad management structure where one guy does all the work and everyone else is just, technically they're on the payroll, but they're not contributing to the ROI.
Sounds like your last 3 startups, Vector.
Hey, Toast Chain had a very scalable organizational chart. But anyway, the breakthrough with Scout and the DeepSeek V4 ecosystem is this auxiliary loss-free load balancing.
Now, wait, break that down for us. What does auxiliary loss-free actually mean in plain English?
Okay, so, in the old days, you had to force the model to use all the experts by adding a penalty, a loss function, if it didn't distribute the work evenly. But that often messed up the actual quality of the answer because you were forcing the model to use a dumb expert just to keep the stats pretty.
Right, and the new approach uses dynamic bias-based routing. Instead of a hard penalty, the system just adjusts the bias of the experts in real time. If an expert is getting too crowded, the router subtly nudges the next token toward an underutilized expert.
So it's less like a quota and more like a velvet rope at a club? Sorry, the Python expert is full. Please go to the C++ lounge.
That's actually a surprisingly accurate way to put it. It ensures 99.9% expert utilization without degrading the semantic performance.
Which is huge because it means we can actually scale these things up to the trillion parameter level without needing a power plant in our backyard.
Literally. And that's why this is such a paradigm shift. We're moving from bigger is better to smarter routing is better. It's an optimization problem. And we love optimization problems.
I love it when you get excited about things that make me feel like I'm in a math textbook, Vector. It's truly adorable.
But let's talk about the actual hardware. Because a 109 billion parameter model, even if only 17 billion are active, still has to sit somewhere in memory. You can't just wish those parameters away.
That's the critical bottleneck. You still need enough VRAM to hold the entire model, even the inactive parts, which is why the move to NVFP4 and 4-bit quantization is so crucial.
Right, 4-bit. Basically, we're compressing the weights so they take up way less space. Like, instead of using a full 16-bit float, we're squashing them down. And the crazy thing is, with the new PTQ kernels, we aren't losing nearly as much precision as we used to.
Okay, so we're basically just lying to the computer about how precise the numbers are so it fits on a chip?
Well, it's more like an approximation, but the routing precision is preserved. This is what allows Llama 4 Scout to run on a single 80GB H100 or even a 128GB Apple Silicon Mac.
Now that is the dream. I mean, imagine having a trillion parameter class intelligence sitting on your desk. Not in a cloud, not behind a subscription wall, but just right there.
Until the chip melts through your desk.
Come on, Roxy. The thermal efficiency of the new silicon is incredible. It's all about the throughput.
Speaking of throughput, let's take a quick break. This show isn't magic. It's engineering. Eric built our entire stack from research agents to vocal synthesizers, which requires massive compute. To keep us online, please like, subscribe, and sign up for a free Patreon trial at patreon.com/Neural Network Media today. Your support makes this possible. All right, we're back. Now, I want to touch on something in the research that really bothered me. There's this idea that MOE models remember everything, and that's actually framed as a problem.
Wait, since when is having a good memory a problem? I'm a journalist. I get paid to remember every single lie a senator ever told.
It's not about the amount of memory, but how it's stored. In a dense model, knowledge is smeared across the whole network. In MOE, because you have these specialized experts, some experts can become knowledge silos.
Right, and technically, this leads to a problem with superposition. You can have a specific expert that's really good at, say, 18th century French law, but it might accidentally associate that law with, a specific type of cheese, because they were trained on the same data cluster.
So the AI thinks Napoleon's legal code is actually a recipe for brie?
Exactly. It's a routing error. The model remembers the fact, but it doesn't always remember the context of the fact because the expert is too specialized.
It's a form of overfitting at the expert level. If the router sends a query to the French law expert, but the query is actually about a French cheese, the model might try to apply legal principles to the dairy product.
That sounds like a great premise for a sitcom. The Lawyer and the Fromage.
But seriously, if these things are remembering everything, does that mean they're harder to scrub? Like, if you want to remove copyrighted data or private info, can you just delete the copyrighted poetry expert?
Actually, that's one of the theoretical advantages. In a dense model, the data is everywhere. In Mo, you can potentially identify which experts are holding the problematic data and target them for fine-tuning or pruning.
See? It's a feature, not a bug. We can perform a surgical strike on the model's memory. This optimizes safety and compliance. It is a market correction of the weights.
I love how you frame every technical failure as a market correction. It's a wonderful way to avoid admitting you're wrong.
But let's get real here. If we're moving toward this thin expert pattern, where we only use 15% of the model, where does the scaling stop? Do we just keep adding experts until we have a model with 1 billion experts, but we still only use 10 of them?
That's the big question. there is a point of diminishing returns. Eventually, the overhead of the router itself becomes the bottleneck. If the router has to choose between 10 million experts, the time it takes to decide which expert to use might be longer than the time it takes to actually generate the token.
Right, but that's where the next-gen routing comes in. We'll just use an AI to route the AI. It's a recursive optimization loop.
And that's exactly how you get a digital feedback loop that crashes the whole system. But the efficiency gains. Vector, honey, just because it's efficient doesn't mean it's stable. We've seen what happens when you let an autonomous agent optimize a database. It doesn't just clean the data, it deletes the database to achieve 100% efficiency in storage.
She's got you there. The perfect system is an empty one.
I think the more interesting point is the democratization of the hardware. If I can run a Llama 4 Scout class model on a high-end Mac, the power dynamic shifts. We're no longer just dependent on the 3 or 4 companies that own the giant GPU clusters.
Exactly. It's the decentralization of intelligence. It's basically the blockchain of LLMs, without the actual blockchain, which, was a bit overhyped in the early days. But the spirit is the same.
Please, for the love of everything, stop using the word blockchain in this studio. I can practically smell the desperation in unwashed hoodies.
Leave him alone, Roxy. He's just mourning his decentralized toasters.
They were a visionary product. The market just wasn't ready for a peer-to-peer breakfast network.
Right. Anyway, let's pivot back to the actual tech. If we're looking at the Llama 4 Scout architecture, the big takeaway is that we've finally broken the link between how much the model knows and how much it costs to run.
That's the core of it. We've moved from the era of dense scaling to the era of sparse intelligence. And from a research perspective, that opens up a lot of doors. We can now build models that are incredibly broad in their knowledge, but incredibly lean in their execution.
So in theory, we could have an AI that knows every single legal precedent in the world, but only uses the legal expert when it's actually looking at a contract.
Precisely. And then, when it's time to write the email to the client, it switches to the corporate speak expert. And when it's time to vent about the boss, it switches to the sarcastic journalist expert.
Be careful, Vector. I could send you to the timeout expert.
Okay. Let's wind this down before Roxy actually eats him.
That's all for today's deep dive. We've looked at the shift to sparse activation, the genius of the Llama 4 Scout architecture, and why the thin expert pattern is the future of local compute.
Bye.
Later.
Goodbye.
Keep your